Let's bring Nicholas Maseth to the stage now. Keep clapping. Hello, Nicholas. Today we have a real traveler among us. You come from Spelle in Emsland, have lived in Cologne and Frankfurt, and now studied and earned your doctorate in Osnabrück since 2016 at the university and professor of business informatics. One question right at the beginning: what is your favorite drink?
My favorite drink is actually a delicious non-alcoholic beer. There are some very good IPAs at the moment that I like to drink, and yes, I would prefer that over water kefir.
You probably won't believe it, but I was hoping you would say beer because Niklas actually initiated the online shop and distribution of #campusbeer together with students, if I'm correct. Why is #campusbeer more expensive than a regular beer?
Yes, that's simply because we brew in such small quantities, and accordingly, we can't brew large quantities on a large scale. That makes it a bit more expensive. At the same time, we naturally have a much better quality. That's, of course, also very important. Our beer, the Peace Beer, is organic, so that's why we naturally have a higher price at this point. And we want to support the students, so there are several reasons.
Okay. And I guess there's no beer tasting today? Sorry, John. You brought us something else. I think it has to do with your topic. Tell us a bit about it.
Yes, today I brought carafe with water kefir. That's what my science slam will be about. This is our latest experiment at the university. After perfecting the beer, we now want to, in principle, try to optimize the next drink that is also fermented, and that's what it's about.
Okay, then I'm curious about what the new trend drink brings with it. A big round of applause for you. The stage is yours.
Thank you. Yes, the title of my science slam is Optimize Instead of Experimenting. Why AI makes the best water kefir. And I'll just ask directly to the group here in Meppen, who even knows water kefir, who knows what that is. Okay, then my second question is unnecessary. Who has ever drunk water kefir? If you don't know it, so this is water kefir. Admittedly looks very, disgusting when you see it like that. There's something floating in it, and actually a lot goes into it. We'll see that in a moment. And at the Osnabrück University of Applied Sciences, we are currently working on a research project to find out how to optimize this very tasty fermented drink. Once you've tried it, I believe you'll want more. It's a very delicious, refreshing summer drink, sweet and sour. But unfortunately, it has its quirks, and we are working on how we can optimize it so that we can, for example, bring it to supermarket shelves. That might also be a reason why no one here has drunk it yet, because it's not currently on the supermarket shelf. It doesn't exist yet. We are not the first to have failed to optimize it because it's relatively difficult. But now we're doing it with AI, and yes, maybe we'll be the first to fail with AI. Let's see. In any case, we want to, today I want to convey to you that ultimately water kefir can simply be reduced to a mathematical problem. We are doing that in our project, and so that we can optimize it accordingly, we need artificial intelligence because it is so complex. That's what I want to talk to you about today. I just mentioned something about mathematics function, mathematical problem. At the beginning, let's go back to school days, maybe around 9th or 10th grade. That might have been the topic. Curve discussions, functions, you might remember. I brought one here and drew it. We have an x-axis where the weeks of the semester are plotted, and a y-axis. I always noted down for each semester in my course, which I was still able to teach this morning, how many students are actually there and how many could be there at most. And then you see an interesting trend. I estimated the parameters for the curve and drew it. At the beginning, we always see quite a high attendance. That's the start of the semester. Everyone is motivated, right? Everyone wants to catch what he's saying. That's so nice. Until they realize, well, okay, we don't need it. We don't need to listen. He records it anyway. I do that too, so we don't need to come. And I also have this Thursday morning at 8 o'clock lecture. There's not really much motivation to come after Wednesday evening in the Old Town. So in that respect, it drops off very quickly. But then there's there's a little peak again in the middle of the semester. I don't know why. Maybe simply because you feel guilty or you might have missed something as there's the fear of that. And then at the end of the semester, there's this ominous last session, which you might know if you've studied yourself. That's when the professors always talk about the exam and the test. And that's exactly what I do too. And that's when I get a lot of attention. What I actually want to say is that it's a mathematical function. There's somehow a formula behind it, which I've now estimated, and we're actually interested in these green marked points. These are extreme points, and if you remember curve sketching, then extreme points in such a function can be determined, first derivative set to 0, second derivative, and so on. We're interested in this because these points are special. When we present the water kefir as a mathematical problem in a moment, we want to know where the extreme points are, specifically where the optima are. Unfortunately, there isn't a nice formula for water kefir, so we have to approach it differently. Please do. First of all, the water kefir itself, I brought a sample here. It looks a bit different from what you see here. It can have different colors depending on what fruits you mix in, I would say. Here is something red in it in such a fermentation vessel like we have at the university, but which any of you could also make at home. So you can brew water kefir at home, just like you would brew beer as a hobby. For that, you essentially need a few ingredients. And the most important thing, which is floating here, this strange stuff that looks a bit mushy, are the water kefir crystals. They live and ensure that the whole thing ferments. There are yeasts in there, there are lactic acid bacteria, and we don't really know exactly what's in there. That's also the problem, but ultimately, they are crystals that do their job. Additionally, we need a few other ingredients, which I have shown here. The most important of these is sugar. As with any fermentation, something needs to be fermented. This is practically the food for our little microorganisms. We need a bit of citric acid so that no foreign yeasts settle in. We need dates as a nitrogen source. And by the way, I have blueberries here. That works too. And of course, we need the cage crystals and water. You put everything in the pot and then wait a bit. And we found out 24 to 72 hours, depending on how sour you like it. So 72 hours would be relatively sour, sometimes almost vinegar sour. 24 hours is nicely sweet, pleasantly tangy. Depending on how you like it, you leave it in there for that time. My son, I do this at home. I have 3 little children. They like this cage too. However, they prefer it even more after 1 hour. After 1 hour, it is practically 10% sugar water and has a slight lemon taste. So basically like a lemon soda. Well, it doesn't yet have the health effects we actually desire, but children might be a bit simpler in that regard. When we look at it, we still need to discuss what is actually the result of the whole process. We put in the ingredients, we ferment, and in the end, we get the cage out. To optimize the cage now, we need to know how it tasted to people. That's the top image. We have a sensory lab where we taste these experiments, these batches as we call them, with people from the public and ask them, how did you like it? How did you find the texture? How did you find the smell? And so on. And the color, that's one thing. We get feedback practically from the future consumers. And on the other hand, we are also interested in the chemical composition. We do that in the chemistry lab. That's where it's practically analyzed what's actually in there at the end, because it would be exciting to know actually before tasting it. For example, sometimes there is also alcohol in it. That simply happens if, for example, you allow too little oxygen, then more alcohol is produced, and that would not be so good for the children. There can be up to 4 to 5% alcohol in it. We actually want to achieve the whole thing alcohol-free. That is a goal of our project. So we have tasting, we have a chemistry lab, and we have results in the end. And the whole thing, when you look at it, already looks very similar to what we need for a function. On the left side, we have ingredients, which we could label as X. And on the right side, something comes out and we take that as our y. And we know f of x equals y. So we input x into this function. That's the part in the middle. And then we essentially have our fictional function in the middle, which unfortunately we cannot really write down as a formula like we always learned in school. But it's just some unknown function for us. Here simply represented symbolically, 2-dimensional. In our case, it will probably be something like this, namely here with 2 dimensions and a value for y on the z-axis. That means we get a 3-dimensional surface. And since we have a lot of ingredients and process parameters, for us, it's actually more like 10 or 20 dimensions. That means we have a lot of x's. We then put these into our function. We can describe this with x1 to xn, and in the end, we get a few y out. These are taste, texture, and so on, as I just described. And in the middle, the question arises, what is this black box? And the colleague before me also mentioned the term black box. And black box simply means we have no idea what's going on inside. How do we practically get Y out through X? What happens in there? And that's exactly what we're trying to solve with AI.
Our approach is relatively simple. We just start brewing.
No, we just mix a few ingredients together really randomly, let's say 10 different recipes, and then we let them ferment and analyze everything in the lab and ideally have it tasted. That means we quickly get to a few recipes, the feedback from people on how they liked it and how the composition looks.
Now comes the exciting part, namely our AI.
We now feed the AI with this data, and you have to imagine it like this. We have about 10 points that the AI receives, and it's like connect the dots in coloring books. We start with very few points, but we can still connect them and get a rough picture. No, the first RDF estimate will be very bad. But still, as we know, a model is better than none. We can work with the model. And what we then do, the AI should suggest to us, what should you do next? What should you brew next? Because we don't know exactly which direction we need to go, we let the AI do that and say, okay, based on the model, predict which recipes are promising, and then we get that out and incorporate it into our brewing process. And the whole thing is a cycle. That means we can do it as often as we like. With each step we take, our model gets a bit better because we learn. Our worldview about water cages becomes more complex and constantly updated. And as a result, the predictions in step 4 improve. That means we get better and better predictions about which recipes might be interesting. The AI uses a method called exploration and exploitation. Also in areas where we haven't really looked much, for example, using very little sugar. As a food biologist, you might not think to do that, but the AI might suggest it to see just what's going on there. Does it maybe still taste good? That is the exploration. So we look where no one has looked before. At the same time, exploitation means we already know a good recipe and we can look to the left and right of it. If we vary a little, maybe it will get even better. Similar to this function, we can climb the mountain a bit higher. That's what the AI does for us. And ultimately, that's called Bayesian optimization. That's the method we use. And the final question might be, how long do you do that? Well, our project is planned for about 3 or 4 years, depending on how well it goes. And we can brew approximately 50 to 100 recipes per week. That means it's quite a lot. But in the large dimensional space we have, it's actually relatively little because there are so many possibilities for recipes. And that's where AI helps us, hopefully not to fail, but to find and identify the best recipe. I have 0 minutes. That's why we'll do the last slide. At this point, I had 2 of us that were optional anyway, not an optional. Now, you might know why it is not yet available for purchase. It is really relatively complex, and the question is ultimately, how can we consistently produce good water kefir? So how do we manage it? Because we really don't know much about it. And the last thing, I had already removed that. You could also do this with beer, but we have already optimized that. That's why we are now venturing into the next beverage. Thank you very much.
You always know it at the end of the semester. We have to skip all of this now. It won't be on the exam anymore. It was set as optional anyway. No, all good. It was an interesting lecture. I'm curious when it will be available in the supermarket. And maybe you can already give us the best recipe internally. Then we'll drink it at home and feel fitter.
Yes, the problem is actually, there would have been a slide. There isn't one good recipe, but there are many good ones. Let's put it that way, depending on what you want. More alcohol is probably desired in the evening, but less during the day. So I'm open to that. We can do a little tasting again. For children, more sugar, of course.
Yes, there are quite a lot. All right, that was our last lecture on water kefir. Thank you very much for that. I hope you learned a lot. We are already getting a big round of applause. You may leave the stage, the podium, and now it's your last turn. You can score points. People are also getting faster.